Hello, my name is Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering at the University of Calgary. And this is Module 3 in our Circuits 2 lecture series where I talk about the properties of a capacitor. And capacitors physically are basically just two plates separated by some kind of dielectric material. And this material could be air in the most sort of primitive sense, but often it's some sort of special material that allows the capacitor to store an increased amount of charge. And so, excuse me, because the capacitor is just two plates, we usually, the circuit symbol is basically represents those two plates. And so that's typically how we draw a capacitor. And now, as current flows through the capacitor, remember, current is the flow of positively charged particles. As current flows from top to bottom through our capacitor, we have an accumulation of positive charge on the top plate and negative charge on the bottom plate. And the collection of positive charge on the top plate and negative charge on the bottom plate creates a voltage. So the voltage and this charge, or the amount of charge stored on the capacitor, are proportional. So we can say that the charge on the capacitor Q, we'll use to represent the charge, is equal to the capacitance multiplied by the voltage across the capacitor. So this is the amount of charge in coulombs. The units for coulombs, the units for capacitance is farads. And of course, the units for voltage is volts. So we don't typically work in terms of charge and coulombs. We like to work instead in terms of current and voltage. And we know that current is the amount of charge that passes through an element per unit time. And so we can convert this equation into a current equation by taking the derivative of charge with respect to time. So current is equal to the amount of charge that moves per unit time. So that's just what the derivative gives us. And if we take the derivative per unit time of capacitance times the voltage, we basically get capacitance, which is a constant, and the derivative of the voltage. And so looking at this equation, this means that, well, actually, I'll just write it in a more compact form. So current is equal to, the current through a capacitor is equal to capacitance multiplied by the derivative of the voltage, or the rate of change of the voltage. And another way to interpret this equation is that in order to get a constant current through a capacitor, we have to have a changing voltage. So if you just have a constant voltage across a capacitor, you're not going to see any current flowing through it. And so there's a classic example that you would have looked at probably in your first circuits course, and that's what happens when you put a sinusoidal voltage across a capacitor. So let's take this example. We've got our capacitor, and some voltage, and we'll say our voltage is equal to a sinusoid, sine omega t. And so if I were to draw that sinusoid, it would, of course, be 0 at 0 time. Oops, that's a little crooked, but anyway, you get the idea. So we have this familiar sinusoidal shape to our voltage. The current, as a function of time, is equal to our capacitance multiplied by the derivative of the voltage. And if we take the derivative of the sine function, we get the cosine function. And so our current is equal to the capacitance multiplied by cosine omega t. And if we were to draw this as a function of time, at time 0, we have 1 times our capacitance. So that's the value at time 0. And then if I can draw this reasonably well, that's not drawn reasonably well, but imagine this is actually a cosine, not this sort of funny thing that I've drawn. And it would have the sinusoidal shape, but it would basically be 90 degrees out of phase from our voltage. And maybe you remember that from your first circuits course as well. The capacitance, essentially the current and voltage through capacitance when we're dealing with sinusoids are 90 degrees out of phase. And we'll talk about this a little bit later on in the course. But the only reason why I bring this up now, we're not going to do steady state sinusoidal analysis at this point. That'll come later. But I just bring this up at this point because this is kind of the classic example that you would have seen, and it does sort of illustrate the fact that, you know, if you've got a changing voltage, then you do have a changing current as well. And we can even sort of interpret this another way. So if we look at time 0, you know, and draw the sinusoid, you know, for negative time as well. If we look at this region right here, this is where we have the maximum rate of change of our voltage. You know, it's increasing. This is where its rate of change is the maximum. And if we look at time 0, that's where we've got the maximum amount of current flowing through our capacitor. Now, if we follow our voltage, it starts to change a little more slowly, and then once we hit our peak, it's basically not changing at all at that particular point. And then if we look at that point in time on our current, that's where our current drops to 0. And so it, again, reinforces this notion that if you've got a changing voltage across your capacitor, you're going to see current. So here we're changing, and here we have current. If we stop changing, the current stops as well. And so that's kind of maybe a more intuitive explanation for what's kind of going on through the capacitor. Now, of course, if current is the derivative of voltage, voltage is the integral of current. And so voltage as a function of time is equal to 1 over the capacitance times the integral from some time t naught to our current time t of our current that changes as a function of time plus whatever voltage we had at time t naught. And all this current is just the, taking this equation and inverting it and solving for voltage. So if current is the derivative of voltage, voltage is the integral of current. So we can do a simple example using this voltage integral equation as well. And so for our example, let's say we have a 2 microfarad capacitor that's charged up to 10 volts, and then it discharges 1 milliamp for 1 millisecond. And so we want to solve for the voltage at 1 millisecond. So t is equal to 1 millisecond. And so we have 1 over 2 microfarads. We integrate from time 0 to time 1 millisecond. We have negative 1 milliamp of current. It's negative because the capacitor is discharging rather than charging. We integrate that with respect to tau. And then our voltage at time 0 is 10 volts. And if you go ahead and do this integral, the value of the integral is minus 0.5 plus 10. So we have 9.5 volts after 1 milliseconds of discharging. And hopefully this also makes intuitive sense because we've got some we've got some charge stored up on our capacitor. It's ready to go. Then we let it flow off of the capacitor starts to discharge, and as that charge leaves the plates in the form of current, we would expect the voltage to drop, and that's exactly what we've got here. It's also interesting to look at the capacitor from the perspective of energy and power. So it definitely takes energy to move charge onto the plates of the capacitor. And the capacitor then, when it stores that charge, is basically storing that energy. And so if you then hook up the capacitor to a circuit and it discharges the charge in the form of current through that circuit, then it's basically releasing that energy. So you can think of a capacitor as an energy storage device. And we're going to be doing a little bit of a practical exercise that will reinforce that. We're basically going to look at whether or not a capacitor is a feasible alternative for a battery. And so if we want to come up with an equation for the power delivered to a capacitor, we start with our normal power is equal to voltage times current equation. So the power delivered to a capacitor, P, is equal to voltage times current. And we're delivering power to the capacitor when we're basically running a current through it, and we're piling up a bunch of positive charge on the top plate and negative charge on the bottom plate. So that takes work, so that's why we're delivering power to the capacitor. If we substitute in our equation for current, we have capacitance times voltage times the derivative of voltage, and this has units of joules per second. And assuming that the capacitor voltage is 0 at time equals to 0, we can then determine the energy stored in the capacitor by integrating the power. Because remember, power is just the amount of energy transferred per unit time, right? And so just to be a little bit more specific about that, so if we want to figure out how much energy is stored in the capacitor, we basically integrate the power that we apply to that capacitor for a certain period of time. Then if we substitute in our equation for power that we have up top here, we get the integral from 0 to t, the capacitance times the voltage times dV over d tau times d tau. The reason why I changed this from dt to d tau is because in this equation down here, we're integrating power with respect to time. And I represent time using the variable tau here. And so I just substituted in tau for dt up there. This is still regular old t, but this represents a certain point in time. It doesn't represent kind of a variable. So our variable time is represented by tau. And our d taus basically cancel here. And so essentially what we're left with is an equation that integrates with respect to voltage. And so the energy stored in our capacitor is just the integral of the voltage waveform from 0 to time t. Now, because we're integrating with respect to voltage, I no longer have t as our upper bound for our integral. Instead, it's the voltage at time t. And so if we solve this integral, this is c times 1/2 v squared. This is vt. And sorry, the lower integral here, this was time 0 before. Now this is basically the voltage at time 0. But we assume that the voltage across the capacitor is 0 at time 0. So this value is basically still 0. And so we've got, we solve our integral, and our lower bound is 0, which is 0 volts at time 0. Our upper bound is the voltage at time t, and this ends up just being equal to 1/2 the capacitance times the voltage at times t squared. Or sometimes we just simplify this. We just say that the energy stored in the capacitor which maybe we'll just write as W, is just equal to 1/2 C V squared. And maybe to add just even a little bit more detail here, the energy in a capacitor at time t. So the energy stored in a capacitor at a particular time t is just equal to 1/2 C times V squared, and this is the voltage across the capacitor at time t. Oops, time t. So this is a nice kind of compact equation, and it's very sort of quick. if we can measure the voltage across a capacitor at any time, and at that point in time, we square the voltage, multiply it by 1/2 C, and that gives us the amount of energy stored in that capacitor. And hopefully that also kind of matches your intuition as well, because we would expect that the more charge we have on the capacitor, the greater the amount of energy it's storing, because we had to do more and more work to put all that charge onto those plates in the first place. And as we increase the amount of charge we have on the capacitor, that also increases the voltage. So bigger voltage means bigger energy storage, basically. And finally, just to sort of talk very briefly about the difference between an ideal capacitor and a practical or real-world capacitor. In an ideal situation, so when we're dealing with, a perfect capacitor, let's say, when we put a certain amount of charge on those two plates, that charge stays there for an infinite amount of time until we hook that capacitor up to some sort of circuit that allows the charge to leave the plates and flow as current. However, practically speaking, if you put a certain amount of charge on a real-life capacitor, you'll notice that the amount of charge just decays over time, even if you don't hook the capacitor up to a circuit. And that's because no capacitor is perfect. There will always be charge leaking between those plates. And if you just leave the capacitor alone, you never hook it up, the charge will eventually disappear just because of leakage through the dielectric between the two plates. And so we can model this in a circuit by representing a real world capacitor as a perfect ideal capacitor with a resistor hooked up in parallel to that capacitor that will allow a certain amount of leakage current to flow between the plates. This parallel resistor has a very high value, but it is not infinite, and it does allow the charge to decay over time. So a real world capacitor then is an ideal capacitor, a perfect capacitor, C, that never ever leaks charge. It's perfect. There's never any charge that flows between the two plates. But then we hook it up in parallel with a resistance, and we often refer to this as a parasitic resistance. And that's where the charge will leak through. So basically you'll have a little bit of current that flows through that parasitic resistance that will eventually deplete the charge stored in the capacitor. And then we would just draw sort of a box around this whole thing. And say this is equivalent to again our real world capacitor. And so for the purposes of this class, when we're doing theoretical questions, when we're doing simulations and stuff like that, you can assume that our capacitors are perfect, ideal capacitors that never leak charge. But we will be doing several things in the course that allow you to also take this parasitic capacitance into account, the parasitic resistance into account. But I will be very clear when you need to take that into account. So if I don't state otherwise, you can just assume that the capacitors we're working with are the perfect ideal ones that do not leak charge.